the semiconductor lesson, how can we motivate the children in this lesson to get some interest in this children?
How a smart mobile becomes so cheaper when compared with a button phone?
Yes.
We can
Yes,
talk
yes.
about the applications, which we use in daily life.
All
Devices.
the electronic devices. So we can ask the children how they are made up of.
Online class.
Huh?
Online class.
Online class. Yeah, online class. How it is possible without semiconductor devices? The communication system itself will not work. Entire communication system will come to a halt if without the invention of semiconductor devices. You can talk
But we
about
don't have communication systems, ma'am. Chapter.
yes, yes.
We don't have a communication system.
We don't
chapter.
have communication system, but communication devices use semiconductors. We can, yeah, communication system is deleted. It's not there. Yes.
Electronic devices is cheaper in cost. Size
Yeah.
is also reduced.
Size, miniature size compared to diode, compared to valves. Previously, they were using valves. Valves are bulky and you need a separate heating system for that. Cathode, anode, grid, all those things. So it's just to introduce the lesson, you can tell about all that. In olden days, how old radio sets, they wouldn't have seen that, no? So maybe in cinemas, they would have seen that radio set. So
Vacuum tubes.
Vacuum tubes, vacuum tubes. You give the instruction of vacuum tubes, then you can start the lesson and you can talk about so many applications of semiconductors, semiconductor devices. You have to talk before you go into all this. So semiconductor, when you introduce it, definitely you have to talk about the resistivity. Metals, you have to differentiate between metals, semiconductors and insulators on the basis of resistivity. And you can talk about different type of semiconductors like elemental, compound, organic, all these are given in the reader. Okay. So on the basis of energy band, anyway, the formation of any energy band, I think they're learning in chemistry. So let us not go in detail. You can just talk about how energy bands are created. So when the atoms come closer, in the case of crystal, atoms come closer, so the energy level gets split up. If you tell that, it is enough. Oh, of course, we did in detail, but other part of the lessons are very important. So the energy level gets split up and we have two energy band, valence band, conduction band. And there are energy levels where no electron exists, where no atoms exist. They are called forbidden energy gap. So electron, electron will not exist corresponding to the energy level. So valence band correspond to some closely spaced energy level. Conduction band correspond to some closely spaced energy level. They are separated by energy gap where no electrons are found. Is it not? So as long as the electron, as the atoms are wide apart, there are definite energy state. Whereas when they come closer, when the atoms come closer to form crystal, due to interatomic interaction, the energy level is split up. All this are explanation for that. So this is a book diagram on the basis of energy band diagram. So this is the basic structure. So you have valence band. So most of the electron at a very low temperature, say at 0 Kelvin, all the electrons will be in the valence band. And EV correspond to topmost energy level of the valence band. And EC is the bottommost energy level of the conduction band. So at temperature, very low temperature, conduction band will be empty. So this is a basic structure. So on the basis of energy band, we classify the substances to metals, semiconductors and insulators. For insulators, the energy gap is huge, greater than 3 electron volt. And there is no energy gap for metal, isn't it? There is an overlapping. The conduction band and a valence band overlap. So always there are some electron in the conduction band, even at a very low temperature. And for insulators, energy gap is less than 3 electron volt. So the band gap, they should never tell the distance between the valence band and the index. It is not the distance, it's the energy. Energy level. Band gap is an energy gap. So you're plotting, this is energy versus the electron. the energy. This y-axis represents the energy. And this question can be asked where plot or draw energy band diagram for an intrinsic semiconductor at T is equal to 0 Kelvin and T at a higher temperature, T greater than 0 Kelvin. So at T, see here, the intrinsic semiconductor is an insulator at T is equal to 0 Kelvin and it is a conductor at higher temperature. So now what you should keep in mind is all the electrons are present in the valence band at T is equal to 0 Kelvin. So now at T greater than 0 Kelvin, see here 4 electrons have gone to the conduction band. So how many holes are created here? How many holes are there?
4
Equal
holes, ma'am.
to
4
electron.
holes, ma'am.
So electron, see, absence of electron is considered as hole. Absence of electrons are considered as hole. So intrinsic semiconductor, the electron which have gone to the conduction band has created a vacancy. That vacancy is only hole. So in the case of intrinsic semiconductor, Ne is equal to NH. So please ask them to mark what is EV and what is EC. So in the energy band diagram, all this marking should be there. So in the case of N-type and P-type semiconductor, so you know the formation you will explain, I'm not going to do that. A P-type and N-type semiconductor. So in the case of N-type semiconductor, what is this 0.01 electron volt, the energy cap? What is that ED here? What is ED here? You are adding some impurity. No, what is doping? Doping is the addition of impurity. So when you are adding impurity, say pentavalent impurity. N-type semiconductors are created by adding pentavalent impurity, isn't it? Correct?
Yes, ma'am.
Yes. So when you are adding a pentavalent impurity, say here, yeah, like here, a pentavalent impurity. So 4 valence electron. So pentavalent, 5 valency, 4 valence electron form bond with 4 silicon or germanium. 1 electron is let free. So it is unbonded free electron. So what will happen to the impurity atom? It becomes because it has 1 electron has come out. With that 1 electron, it was neutral. So it is a positive ion with an electron. So when you are representing N-type semiconductor, you should represent as positive ion with an electron. N-type semiconductor is represented like this. So when your formation of P-type PN junction, you will represent N-type is always represented as a positive ion because this N-type impurity has donated 1 electron, isn't it? And then you can always, this is an electron here. So you can write this electron. For every ion, for every impurity atom, we are adding pentavalent impurity. 1 electron is spent. Similarly, trivalent impurity. If you are adding a trivalent impurity, now
One shortage.
yeah, 1 shortage. So here when you are adding a trivalent impurity, yeah. So trivalent like aluminium plus 3. So 1 hole is created. 1 hole is created. So with this is a vacant space is there. So the immediate electron from the other side will jump. And then when electron is moving here, a hole is created. So now this acceptor, this is called acceptor impurity. So with this plus 3, this aluminium, no, trivalent impurity is a neutral one. But now when it is getting 1 electron, it is becoming a negative ion. It's becoming a negative ion and 1 hole is created. So you have to draw an P-type semiconductor with a negative ion and hole. Do you think P-type and N-type has only electron? P-type semiconductor has only holes, no electron, and N-type semiconductor has only electron and no holes?
No, in a P-type semiconductor, holes are majority charge carrier.
Yeah. So there are majority carrier. N-type majority carriers are electron and minority carriers are holes. Okay. So now how to draw the energy band diagram for the N-type and P-type semiconductor? How will you draw? That's very important when you are instructing the children. They have to draw the donor energy level. So for n-type, donor energy level is just below the conduction band. So the donor has large number of electrons, isn't it? 3 electrons. So the electrons, it is easy for the electron to go to the conduction level. So very low energy is required. That is 0.01 electron volt energy only required. Whereas this energy gap will be very high. For intrinsic semiconductor, for silicon it is 1.1 and for germanium it is 0.7 electron volt. Now see how much energy is required for the electron and the donor energy level to move to the conduction band. So here large number of electron become available in the conduction. So large in a conduction level means large number of electrons are available. So and in the case of p-type, the acceptor energy, see the impurity atoms are acceptor impurity because they are accepting electron. The acceptor energy level, that the acceptor electron energy level is very close, just above the valence band. It is only 0.01. Here what happens is the electron from the valence band, always valence band is completely filled at low temperature. At higher temperature, what happens? Very low energy is required for the electron from the valence band to move to the what level? What is this level called? What is this level? EA. This is donor, no? Donor. Pentavalent acceptor. So here what happens when the electron, so large number of electron go to the, that's what happens, aluminum gets 1 electron extra. So all the electrons go to the donor level. So if 8 electrons are going to the donor level, acceptor level, how many holes are created here? That many holes are created here. So the p-type semiconductor, holes are in the valence band. The holes, the p-type semiconductor, the majority carriers are in the valence band. Whereas in n-type semiconductor, the majority carriers, electrons are in the conduction band. That difference you should make the children understand. The holes are always holes, in a p-type semiconductor, holes will be in the valence band. They should mark the donor level, acceptor level, and the energy difference is very, very small between the valence band and the acceptor energy level. This one you should make them understand. For all these points, mark will be given. So now after making them understand p-type and n-type, we have to go to so in the case of intrinsic semiconductor, what is the relation between Ne and NH? Intrinsic semiconductor. What is the relation?
Equal.
Equal. So how many electrons are removed from the lattice side? That many holes are created. So here in the case of extrinsic semiconductor, the relation between Ne and NH will be NH is equal to Ni square, where Ni is the intrinsic charge carriers. So in the n-type semiconductor, there are intrinsic carriers. Okay. So NH is equal to Ni square. This is a relation. Okay. So you have a problem based on this. A pure silicon crystal has 5 into 10 power 28 atoms per meter cube. Okay. It is doped by 1 ppm concentration. What is ppm? What is ppm?
Million.
Parts per million. Concentration of pentavalent As. Calculate the number of electron and holes. Ni is given. So now in order to get any pentavalent impurity, so Ne is equal to Nd, isn't it? Ne is equal to number of donor atom. Every donor atom gives 1 electron. So how will you calculate Ne? So number of atom available is 5 into 10 power 28. Okay, it is doped by, for every 1 million atom, 1 pentavalent impurity is added. So number of pentavalent impurity will be 5 into 10 power 8 by 10 power 6. So every yes. So 5, do you understand this? How to calculate the number of electron? So
Yes.
Ne is equal to 5 into 10 power 8 by 10 power 6 because the impurity level is 1
10 power
ppm.
28. 10 power 28 is
10 power
28 is
28 by 22, no? 5 into 10 power 22, Ne. Am I correct? Yes.
yes, ma'am.
You have to find out number of electron we found out. Number of holes can be found out from this formula. NH is equal to Ni square. Already Ni square is given, which is Ni square is 2.25 to 10 power 32 divided by this. So this will be number of holes. So in this case, Ne is much larger. Ne is this much. NH is this much. Carbon, silicon, and germanium have same lattice structure. Why is C insulator and Si and Ge intrinsic semiconductors? So all of them have
related to the energy gap between the valence and conduction bands.
maybe, but if you consider the valency of all the three are 4, but this 4 valence electron for carbon. Okay, for carbon, the 4 bonding electron of C, Si, and Ge lie in the N is equal to 2 level, isn't it? Correct? For silicon, it is N is equal to 3. For germanium, N is equal to 4. So the outermost electron lie. For carbon, it is N is equal to 2. Lie in N is equal to 2. For silicon, N is equal to 3. Germanium, N is equal to 4. So now the ionization energy will be more for carbon or for germanium. Ionization energy is energy required to remove the electron, isn't it?
Carbon,
so carbon, it is more because it is in the lowermost level. N is equal to 2. So the energy required. So energy required to take out an electron from these atoms, that is ionization energy, will be least for germanium. So ionization energy, that is ionization energy, is the energy required to remove the 4 electrons in the outermost shell, is least for germanium and maximum for carbon. And among the silicon and germanium, germanium will be a better choice because, as you say, as Aparna says, the energy gap itself is decided by the bonding electron, where they are located. The bonding electron, if they are located in a comparatively higher orbit, then it is easy to remove the electron. Okay. Yes. For germanium, it is easier compared to silicon and germanium. The ionization energy of germanium is least. Silicon, it is slightly more, and C has a maximum ionization energy. So what are the 2 processes that can get initiated when a PN junction is formed? What are the 2 processes?
diffusion, ma'am.
Drift and diffusion. Drift and diffusion. And can we take a p-type semiconductor and n-type semiconductor and join them to form a PN junction diode? Is it possible? Is it possible? Suppose I want to create a PN junction. I'll take a slab of p-type semiconductor and then attach with the physically. Can I attach? Physically, can I attach these 2 and create a PN junction?
No.
No, it's not possible because why? Why?
Junction.
At the junction, at the atomic level, there will be discontinuity. So I want the electron and hole to move across the junction. This is a junction region. So there will be discontinuity at the atomic level. See, just physically, when you see, they will be together. The junction, there will be continuity. But when you see through a microscope or a powerful electron microscope, they will be well separated. Atomic level, there will be a distance of several atomic distance separated. So there is no connectivity made in the atomic level. In the atomic level, there will be a discontinuity at the atom level, at the atomic level. Okay, so you cannot physically join them. Okay. So the answer is given in the textbook. Any slab, however flat, will have roughness much larger than the interatomic crystal spacing. And hence continuous contact at the atomic level will not be possible. Okay. So continuous contact at the atomic level will not be possible. Okay. So discontinuity will be present. So what is done is you just grow a you take a thin layer of p-type semiconductor on which you add an n-type impurity. You add a p-type, take a p-type semiconductor and then add n-type into pentavalent impurity. By diffusion, then melt the pentavalent impurity, heat it, p-n junction will be formed. Okay, p-n junction will be created. This is the way we have to create a p-n junction, not by attaching a p-type and n-type together. Okay. So now the two processes which get initiated are diffusion and drift. What is the difference between diffusion? First, we have to talk about diffusion only, isn't it? What is diffusion? What is a diffusion? So, you know, when you're drawing, please draw this diagram. So, you know that this is a p-type material. P-type material, you just, you're denoting by a negative ion and holes. And there are few electrons too. I've denoted by few electron also. Similarly, n-type semiconductor is denoted by positive ion and electron, isn't it? Positive ion and electron. So what will happen as soon as a p-n junction is formed? What is diffusion current? Diffusion. So in n-type conductor, electrons are hole. Electrons are majority electron here, minority hole. Here in this region, majority are electron, minority hole. In p-type, majority hole and minority electron. So due to concentration difference, due to difference in concentration, electrons will, see, electrons are more here, electrons are less in p region. Holes are more here, holes are less here. So due to the difference in concentration, electron and hole move across the junction. Okay, so majority carriers cross the junction. That is only diffusion current. Diffusion current is because of the movement of majority carriers across the junction. Okay, so now what will happen after this? This is the first process. Okay, so here when an electron diffuses from N to P, it leaves behind ionized donor on the N side. So near the junction, what happens is this region. So it was rich in electron previously. Now the electron has been diffused to the P region. So near the junction on the N side, positive ions are seen. And near the P side, what happens? Why this is getting depleted? There are no holes here. Why there are no holes? There are no electron here. What happens to these holes and electron? Am I audible?
Yes, ma'am.
What happened to the electron and hole near the junction?
Transferred.
Transfer. They have diffused, isn't it? So near the junction, this diffusion takes place so fast. Okay. So the diffusion electron from this junction has moved to the P region. Holes have moved to the N region. So near the junction, this process took very fast. So the region on either side of the junction got depleted of what? Depleted of free charge carriers. So what happens is this creates a negative potential. Negative potential is created near P side near the junction. Positive potential is created on the N side near the junction. So what will happen now? Will that if you once this depletion region is created, it creates a potential barrier. This one is known as potential. It's not a battery, it's a potential barrier. So what is the effect of potential barrier? What will happen after the potential barrier is created? Can electron move to the P region? Hole move to the N region?
Depletion layer may be changed.
So a depletion layer is formed. So electron will be repelled by the negative potential here, and the hole will be depleted by the positive potential, isn't it?
Yes.
Correct?
Yes, ma'am.
So majority carriers motion will stop. The motion of majority carrier will stop. Diffusion current will stop. Okay. But there are few holes here, isn't it? There are few holes in the N type. These holes will be attracted towards this negative potential. And in P type, there are few electrons. This electron will be attracted towards a positive potential. So now minority carriers. So first diffusion current was due to majority carriers crossing the junction. Because of the diffusion current, the region on either side of the junction got devoid of free charge carriers. But these immobile ions created a potential barrier. This potential barrier now is going to facilitate the movement of what type of carriers? Now, after the potential barrier, what type of carriers will cross?
Minority carriers.
Minority carriers. So minority carriers crossing the junction will give rise to drift current. Drift current. So now, if you see this diagram, yeah. So now see this diagram. So this is N type semiconductor. This is P type. Sorry, this is P. This is N.
Left side.
Depletion. P region, N region, and this is a depletion region. So what was diffusion current? Diffusion current direction was this side, isn't it? From P hole. So this is the diffusion current. This is diffusion. So now drift is, this is drift.
Opposite.
Opposite. So diffusion current, first diffusion current will be large. Later on drift current will be large. And once a PN junction attain equilibrium, okay, when soon the diffusion current will cancel the drift current. So no current will flow across the junction. Okay, so now the diode has been formed with the depletion region. There will be a depletion region and no all the current will stop. Diffusion will stop, drift current will stop. Now we say that the diode has attained the equilibrium. So all this process the student should explain. I will tell you how to, what are the easier, what are the steps students should remember. First, they should talk about diffusion current, formation of potential barrier, drifting. Okay. So then finally they should conclude the process continues until the diffusion current equals the drift current. Thus a PN junction is formed. In a PN junction under equilibrium, there is no current. There is no current. They should not see when the question is about formation of PN junction, let them not connect any battery. The students have a tendency to connect the battery, no way. And they should, when they are drawing this slab, this black line indicate metal contact. This black line, because it is an insulator. Our semiconductor is a insulator. It's a so any in order to connect to the external circuit, always there will be a metal contact at the end. So this diagram. So on the P side, negative potential, on the N side near the depletion region, positive potential. The potential difference is called as a potential barrier. So this diagram represent that. So this again a book question. Can we take one slab of P-type semiconductor and physically join it to another N-type semiconductor, get a PN junction? So all the example question we should give importance, because in our exam there is a greater probability of asking these questions. So any slab, however flat, will have roughness. So you may think that this surface, the surface, this junction is flat. But if you take microscopically, if you analyze now, the roughness much larger than the interatomic crystal spacing. So the spacing, the spacing becomes more than 2 to 3 Armstrong unit, and hence continuous contact at the atomic level will not be possible. So you can write there will be discontinuity for the flow of charge. Discontinuity. The charges will experience discontinuity. They have to travel. For the charges is a very long distance. Very long distance. A 2 to 3 Armstrong unit is a distance. They are not only if they are close now due to intermolecular attraction, they will cross or they will cross the junction. So when the distance is more than 2 to 3 Armstrong unit, they will not travel. Now we come to biasing. So what happens is the circuit diagram. Let them draw a simple circuit diagram forward biasing or reverse biasing, they should join a voltmeter, ammeter. For forward biasing, it is in MA and microammeter. Reverse current is, forward current is due to majority carriers. Reverse current is due to minority carriers. Okay, and this graph. So this is knee voltage, isn't it? This one is knee voltage. What is knee voltage? Forward voltage at which the current increases sharply. At this voltage, the current increases sharply. And a diode is a non-ohmic device. Why it is a non-ohmic device? Diode is a non-ohmic device. No, all electronic diode or LED or transistor, they are all non-ohmic.
Current won't depend. Temperature, because of temperature.
Yeah, PI characteristic, PI graph is not a straight line. Okay. And see here, when you reverse the voltage, no, it behaves differently. Current depends on the sign of the voltage. And you have to explain this, what is the breakdown voltage here? The reverse current is independent of voltage because the reverse current, no, whatever small current which flows is independent of voltage, always almost constant. You will get a constant value. Very small value because the reverse current is due to minority carriers, isn't it? And what is the breakdown voltage? When you apply a high reverse voltage, what happens is the electric field is so high that it ruptures the covalent bond. The covalent bond itself gets ruptured. So a large number of electrons get they move away from the lattice. So you have this is a lattice structure, isn't it? So these electrons, because of the high electric applied reverse voltage, all the electrons come out and a huge amount of current will flow at breakdown voltage. So now we should never allow we should never operate a diode under reverse voltage because of the high current. The whole conductor or the whole diode will get heated up, and it is a current temperature sensitive device. Diodes are temperature sensitive, isn't it? Okay. So in this, we learn about minority carrier injection. What is that? During forward biasing, what happens? During forward biasing, see what happens to the width of the depletion region during forward biasing? This is a depletion region, no?
Increases.
It decreases. It decreases. Why? Because this is the V applied voltage. This is applied voltage and potential barrier is this. So the applied voltage opposes the potential barrier. Applied voltage and potential barrier in the opposite direction. So this width of the depletion region get reduced. So here the electrons, the end region get attracted towards the applied voltage. So initially you know that when the applied voltage is less than the barrier voltage, there is no current. If the barrier potential is say 0.7, till you apply 0.7 volt, there won't be any current. So if the applied voltage becomes more than the barrier potential, the electron will be attracted towards the positive of the battery, applied voltage, and hole will move. So electron and hole will cross. So now electron and holes are majority carriers. Electrons are majority carriers here, holes are majority carriers. So the majority carriers, the electron will get injected to P region where they are minority. Okay, so this process under forward bias is known as minority carrier injection. So minority, say electrons which are majority in the N region get injected into P region where they are minority. So minority carriers get injected, holes get injected in the N region. Electron will get injected in the P region. So that process is known as minority carrier injection. One board exam, this question was asked. Okay, so now see what is the significance of this graph. So as you increase that voltage, no, V naught, what happens to the barrier height? Barrier potential reduces, no? Previously it was this much. Now, as you increase the applied voltage, the barrier potential is decreasing. Okay. Barrier potential without battery is this much, E naught. So low battery voltage and high voltage. So low voltage is this and high voltage. See, low voltage, the barrier potential is not reduced that much here. So now this is the V naught barrier height. Okay, original one without battery. Now at low voltage, this is becoming up to this. And when you increase the voltage, the barrier height is decreasing. That is the significance here. Here the P side negative. This is negative. This is positive near N side. So here this corresponds to this potential and this corresponds to this potential. So this is the significance of this diagram. So now you know the current under, see here, under reverse biasing. What happens under reverse biasing? So now my applied voltage and the barrier potential. So this is a barrier potential and applied voltage. Both are in the same direction. So now what happened? See here. Previously, this is the barrier. This is the V naught potential barrier. Now what is happening to the height of the potential barrier? What happened? It is increasing. It is increasing. It is increasing now. Okay, because the applied voltage and the barrier potential both are in the same direction. So can electron see the electron cross the junction? Hole cross the junction? Can they cross the junction? Majority carriers, can they cross the junction? Only when they cross the junction, I tell that there is a current. Will they cross? Why they will not cross? Why they will not cross? Electron from N region, can they cross the junction and move to the P region?
Because of potential barrier.
So they find this negative. No, here the potential barrier is also negative. The applied voltage is also negative. So electrons are going to be repelled. Holes are going to be repelled. So they're not going to cross the junction. But in this N region, there are few holes, isn't it? There are few holes here. And P region, there are few electrons. Minority carriers. Can minority carriers cross the junction? Can they? Yes, no?
Yes, ma'am.
So,
very less.
Very less. So minority carriers under reverse biasing, minority carriers will cross.
ट्रेन चल गई है क्या काम है
Okay, so that result in current. So minority, when minority carriers are very less, the reverse current will be very, very less. That is why you are having a microammeter only can detect. Microammeter only can detect the reverse current. So
Micro also negligible.
so when an external voltage is applied across the diodes, as that N side is positive and P side is negative, it is said to be reverse biased. Sometimes they ask what is forward biasing, what is reverse biasing. Okay. So the applied voltage mostly drop across the depletion region. The direction of applied voltage is same as the direction of barrier potential. As a result, barrier height increases and the depletion region widens. Okay, so the effective barrier height becomes V naught plus V. V naught is a barrier and V is the applied voltage. So thus diffusion current decreases compared to the diode and the forward bias. So that result now, what type of current flows? Diffusion current will not flow. Only drift current of the will flow. That is, drift is due to minority carriers. Minority.
Voice is not clear, ma'am.
Voice is not clear, huh? Sorry?
Some disturbances are there.
Wait.
Some. Now clear, ma'am.
Now clear, huh?
Yes, ma'am.
Now clear, okay. Maybe when I'm sharing, slide sharing, it is coming like this.
Okay. Now clear, ma'am.
Now clear.
Yes.
Now I think basically the process up to formation of PN junction it's clear. Now I think we can go to the questions. So as I am doing the questions, we can discuss. Okay. Name any two factors on which electrical conductivity of a pure semiconductor depends. What do you think?
Temperature.
Temperature and doping. Is there any disturbance now?
Ma'am, they have given pure semiconductor, so does
Okay.
doping-
Okay, doping. No, temperature and type of semiconductor like silicon and germanium. Conductivity of germanium is better than silicon, isn't it? It depends on temperature
And conduct.
and the type of semiconductor. Why does the conductivity of semiconductor increase with rise in temperature?
Because generally insulators, when increase in temperature, its conductivity also increases. Like that, ma'am.
Yes, but there is an energy gap, no, for semiconductor. So the thermal energy, because of the thermal energy, the electron overcome the energy gap and move to the conduction band. Okay.
That is also property, ma'am. One of the property you can see.
That's also property, energy gap. So we can also write energy gap, isn't it, for the first question? First question, name any two factors on which electrical conductivity of pure semiconductor depend. We can write temperature and energy gap. Why does the conductivity of semiconductor increase with rise in temperature? That's what the thermal energy will overcome the energy gap. The electron can overcome acquire energy to move to the conduction band, isn't it? At lower temperature, all of them are going to be in the valence band, all the electrons. So at a higher temperature, they gain energy and move to the conduction band. So the conductivity of semiconductor increase with rise in temperature. Am I correct?
Yes, ma'am.
Yes. So you have to supply energy. So either in the form of, sometimes if you can also supply light. So when light of suitable frequency fall on a semiconductor, the electrons in the valence band can be excited to the conduction band. So there also the light energy is used to overcome the energy gap. So it can be in the form of light or in the form of applied potential difference or in the form of heat. Okay. What is doping in a semiconductor? Why is it done?
Adding of impurities.
Adding of impurities.
Okay, adding of impurities. Why is it done?
Because of to increase the electrical
conductivity.
To increase the conductivity. To increase the conductivity. So similar question we discussed. Carbon and silicon are known to have similar lattice structure. However, the 4 bonding electron of carbon are present in the second orbit, while those of silicon are present in the third orbit. How does this difference result in difference in their electrical conductivities? So when n is equal to 2, the ionization energy for carbon is more than the ionization energy for silicon, isn't it?
Yes.
So energy required to remove bonding electron from carbon is more than the energy required to remove bonding electron from silicon. Same thing we discussed, isn't it? Silicon and germanium. This one we discussed. What happens to the width of the depletion region when it is forward biased and reverse biased? Width of the depletion region under forward biasing. Easy question, no? It reduces, isn't it?
Yes.
See, whenever we draw a PN junction, please draw like this. That is the basic thing you should draw. P, N, and this is a junction. Near P type, it is always negative. And this is plus. So put a battery, fictitious, we call it as a fictitious battery. This is structure basically. So under forward biasing is, this is correct. Correct. So when we connect P to positive and N to negative. So this is applied, this is V naught and this is V. So when V is more than V naught, what will happen? The electron here, electrons are, number is more, few holes. Here, hole is more and few electrons. So electron and hole will cross the junction. So when they are crossing the junction, what will happen is, so they are going to cross the depletion region. So what will happen? This region will be filled with electron and hole. Okay. So the width of the depletion region, they are going to come closer. No, the electron is going to come closer to the junction. Holes are going to come closer to the junction. So the depletion region width will decrease. Under forward biasing, width of depletion region, what will happen? It will decrease. What will happen under reverse biasing? These holes will be attracted towards, see, under reverse biasing, they will, under reverse biasing. What is reverse biasing? What is reverse biasing?
Negative to
P type is connected with the
P type is connected to
positive.
negative charge.
And N is connected. So what will happen to the holes here? And what will happen to the electron here? The electron will move away from the junction. They will be attracted towards positive. Holes will be moving away from the junction, isn't it? Because they are attracted towards negative. So more and more
Depletion
region will widen up now.
Yes,
The
increases.
depletion region will widen. So now this will widen because they move away from the junction. So here the electron and hole move towards the junction. When they move towards the junction, this width will decrease. Whereas during reverse biasing, the holes and electron will move away from the junction, increasing the width. Okay, very, very important question. This is also very, very important. How is a sample of an N-type semiconductor electrically neutral, though it has excess of negative charge carriers? So how do you represent a N-type semiconductor? How do you represent an N-type semiconductor?
Majority electron.
Plus. Correct. Pentavalent impurity is arsenic. What is arsenic valency? 5. Am I correct?
Yes, ma'am.
So it forms bond with 4 silicon or germanium.
Germanium.
Okay. Now, after forming bond, 1 electron is let free. So now this has lost 1 electron. Arsenic inside the silicon lattice, it is forming 4 bond with 4 silicon, and 1 electron is let free. Okay, this is free electron. But this electron charge, so once the arsenic has lost 1 electron, it becomes a positive ion. So the charge of the positive ion of arsenic cancel with the charge of the electron. Okay, so though there are free electron, it is neutral. N-type is neutral because the charge of the electron cancel with the charge of the positive ion of the donor impurity. So you can write the charge of free electrons plus charge of donor impurity. The donor becomes what type of ion? Positive ion, isn't it? The donor, it is donating 1 electron. See, with the 5 valency, with 5 electron in the outermost shell, arsenic is neutral. When it is donating 1 electron, when it is letting loose 1 electron, it becomes a positive ion, isn't it? So when it is losing 1 electron, equal amount of positive charge is created. So those two will cancel. Same explanation you should give for P-type. Even P-type semiconductor is electrically neutral. How to explain that P-type? P-type is how it, what are P-type impurities? What are p-type impurity? Aluminium, boron, correct? So aluminium will form bond with this one, and this one is free here. Correct? This one is free. There is a hole, but electron from this one will move here. So now this aluminium is getting one extra electron, isn't it? And this create a hole here. From where this electron has come, one hole has been created here. Am I correct?
Yes, sir.
Yes. So which two charges cancel each other? Which two charges cancel each other? So this aluminium becomes a negative ion. Aluminium, because it is getting one extra electron, and there is a hole. There is a positive ion. So this positive ion of the hole and the negative ion, charge of the negative ion, become added up to give neutrality. So for every aluminium atom added, one hole is created, and aluminium is not an atom now, it becomes an aluminium ion. That is why when you are indicating, this is the way you represent n-type with an electron here. Positive ion with an electron, and p-type is always denoted by negative ion with hole. Okay, so the charges get cancelled. The charge of the hole plus charge of the negative ion nullify the charge, total charge. Okay, next. How does the energy gap in an intrinsic semiconductor vary when doped with pentavalent impurity? What happened to the energy gap? It increases or reduces?
Reduces, ma'am.
Reduces here. Now, this is valence band. This is conduction band, correct? Now, in the case of n-type, so this, let us say for intrinsic semiconductor, it is about say 0.7 electron volt. Now here, there is a donor level. The donor impurity level, this is EC and this is EV. So now this 0.7 electron volt is reduced by a factor of this. Now the donor energy level is reducing. See now there are in the donor large number of electrons are present, isn't it? Now what is the energy gap here? So only this electron is going to the conduction band, no? This electron will move to the conduction band. And the energy gap is only how much? What is the energy gap? This energy gap is only 0.01 electron volt. Correct? This is only 0.01. So energy gap which was 0.7 electron volt. In the case of intrinsic semiconductor, the electron, you have to supply energy in order that electron move from conduction band to the valence band to the conduction band, crossing this 0.7 electron volt, isn't it? Correct? In order that conduction band to get extra electron, you have to supply energy so that valence band electron get excited to the conduction band. Whereas when pentavalent impurity is added, this ED, no, it's very close to the conduction, EC. So even as energy of 0.01 electron volt is sufficient for the electron to move to the conduction band. Is that point clear? So what is ultimate effect is the width of the this one, the energy gap get reduced. Okay. Okay. How is forward biasing differ from reverse biasing? Two differences you should tell me. First, we can tell about the connection. Correct? In forward biasing,
P-type is connected with the
positive and n-type is connected to negative, and reverse biasing p-type to negative. Okay, then what is
current will increases in forward bias, whereas in the reverse bias
current is
only
less.
microampere.
Yeah. So in the case of forward biasing, majority carriers will cross the junction. So current is more. Forward current is more than the reverse current because forward current is due to the crossing of majority carriers across the junction. Reverse current is due to what?
Minority carriers.
Minority carriers. And resistance which case it is more?
The
Forward
reverse
bias, reverse bias. And the resistance offered by the diode is more in reverse biasing than in forward biasing. One more also you can write. What is another one? What happens to width of depletion region during forward biasing?
less, ma'am, compared to reverse
Compare.
bias.
Width of depletion region decreases in forward biasing and increases in reverse biasing. So explain how depletion region is formed in a junction diode. Many board papers, it's a repeatedly asked question. So this is a very short, I have shortened the answer. So they can talk about two important processes occurring due to the formation is diffusion and drift. During the formation of PN junction due to the concentration gradient. That is very important. Majority carriers cross the junction because of concentration gradient. Gradient means what? As you move from N to P, N, the concentration of electron is more. And P, the concentration of electron is less. So the electron will move from N to P. Holes diffuse from P side to N side and electron diffuse from N side to P side. This motion of charge carrier gives rise to diffusion current. So when electron diffuse from N to P, it leaves behind an ionized donor on N side. So they will draw the diagram, at least a rough diagram they should draw. So here, what is created? Leaves behind an ionized donor on N side. So as electron continue to diffuse from N to P, a layer of positive charge. So positive charge is created. So when the holes are diffusing, it creates ionized negative near the junction on the P side. This phase, so now this is only depletion region. Sometimes they ask only how a depletion region is formed. So they should talk about diffusion current. Okay. So as the electron diffuses from N to P, it creates a layer of positive charge, positive ion near the depletion region. As holes move from P to N, so this region get depleted of holes. So it is a acceptor impurity, that is a negative ion. Okay. So this negative ion on P side, positive ion on N side create a potential barrier, and that is only depletion region. Potential barrier is formed and a depletion region is also created. So the space charge region on either side of the junction together is known as depletion region. Space charge means there is no free charge carriers near the junction. So this is a diagram. Okay, now this is also repeatedly asked question. In the following figure, the diodes which are forward biased are. What about the diagram? Is it forward biased? Both are connected to positive. P is also connected to positive. N, this is a symbol, no? PN, symbol of diode. But P side is more positive compared to N side. P side is more positive to N side. Okay, so we can call this as FP only, forward biased. Now, this is a zero earthing and this is a negative. What about second one? P is connected to minus 10 volts and N is connected to 0 volts. Huh? What type of biasing? Reverse biasing. Good.
Biasing.
Reverse bias. Now, P is connected to minus 5 volt and N is connected to minus 12 volts.
Reverse bias.
Is it reverse? P
Negative
is less
to
negative compared
positive.
to
Positive to
forward. So you compare relative, it is only relative. See, both are negative, but P is less negative compared to N, isn't it?
minus 2.
Minus 5. Minus 5 is less negative compared to minus 12. Here, reverse. Reverse. Definitely reverse. Reverse. This is reverse bias. Okay. So now we teach them the application of PN diode as a half wave rectifier. So when they draw the diagram, they should be very careful. So when they are drawing this diagram, it's a primary of the transformer. So they should necessarily draw a step down transformer. Very important. Primary coil, the number of, because this should have number of turns in the secondary should be less. That they should draw. Okay. So number of turns in the second, it's a step down transformer. So what is a rectifier? It converts AC to DC, isn't it? AC to DC, all the explanations. See, in this type of question, what they expect is the circuit diagram should be pakka. 1 mark will be given for circuit diagram. Okay. So during positive cycle of AC, okay, A will be forward biased. So it will contact, the diode will contact. The diode will contact only when it is forward biased. That is the basic principle of diode being used as a rectifier. Only when the diode is forward biased, it contact. When the diode is reverse biased, it will not contact. So during positive input, diode contact. During negative input, the diode will not contact. And then the waveform, the negative half cycle of AC, the diode is reverse biased and it will not contact. That's all. Simple explanation with this graph, input graph, output graph. So here, power is only 50% of the input power, isn't it? Power is only 50% because only 1/2 cycle we have power. That is a disadvantage. So we get output power only across half cycle.
How much, ma'am, that is?
Which one?
How much power?
This, see, suppose if they ask now 3 marks, now this will carry 1 mark, the circuit diagram. This
No,
graph, this will
Ma'am,
get 1
the
mark.
output power half you are telling, no, ma'am.
Yeah.
Maybe
Suppose
40%.
100 watt now, 100 watt is the input power, input voltage power now, you will get only 50 watt. Output power will be 50 watt.
Suppose if they'll ask efficiency, ma'am.
50% only, no?
41.6. I think.
Yeah.
40,
Efficiency, how do you define efficiency?
40.6, sir.
Power by
Output by input, ma'am.
Output by
Output
input.
by
In
input,
terms.
no. Output by input.
Ma'am, 40.6 correct, ma'am.
How are you getting that? How are you getting that? It's only 50% of the, that's what given in the
No,
reader,
no,
isn't it?
in one book I referred, ma'am, 40.6 for half rectifier.
Oh,
Yes,
maybe.
in state board books, it will be 40.6.
Okay. Now
Full wave
it
rectifier
is
means
CBSE, but I
81.2.
don't have, actually, I
wave
don't have any
rectifier.
idea about it. Power is reduced here. We get reduced power.
Yes, ma'am, in the state board book they given, ma'am, 40.6.
Yeah.
Yes,
No,
sir.
that's see the data that is not available in the CBSE, they won't ask you.
Won't ask.
They won't ask. See,
Okay,
actually,
ma'am.
for explanation, 1 mark, and graph 1 mark will be given, and then circuit diagram 1 mark.
Graph half mark will know, ma'am.
They may even give 1 mark. I have corrected papers where 1 mark they give input half mark, output half mark. Okay.
For
And full
diagram
wave.
1 mark.
Diagram definitely 1 mark. Sometimes they even give 1.5 marks.
Now for us only 3 marks was, you know, ma'am.
3 mark question. That's what if they ask this question now, they may even give 1 mark for this, 1 mark for the explanation, 1 mark for the graph. So the center tap transformer, there's only the difference. You have 2 diodes and you have a center tap that they have to explain. So one of the diode will be forward biased in any of the cycle, isn't it? So you can even draw a book diagram. Say book diagram, they would have given 3 this one. So input at A, this is input at B, and this is output. So input at A, if it is like this, so A will be forward bias, so I get output. Now input B at B will be out of phase, isn't it? So now when the input A is, this is due to D1, so the output is D1. So now during the negative half cycle, so this also you can give one more graph. This is the input. This is at the primary. input, AC input. So when the input is positive, input at A is positive, input at A is positive, input at B is negative. So diode 2 will not conduct, D2 will not conduct. Now input power is negative, input voltage is negative, input at A is negative, but input at B is positive. So D2 will conduct. Similarly, for the next cycle, D1 will conduct. Next cycle, D2. So during positive cycle as well as negative cycle, we get input. So this is a diagram given in the book, isn't it? In the book diagram, input at A is given and input at B. So the input at A and B are out of phase by 180 degree. So one of the diode will conduct during positive cycle as well as negative cycle. So next we come to LED. The question will be, mention the important consideration required while fabricating. So whenever you are teaching this optoelectronic devices, fabrication is very important. How a diode is fabricated. The case of LED, it is fabricated with a transparent window, isn't it? Transparent window. That I have not given. So LED, what is given in the reader is, you have the reader with you? LED. So it is a heavily doped. So heavily for fabrications, if they are asking now, heavy doped. Heavily doped PN junction which under forward bias emits spontaneous radiation. The diode is encapsulated with a transparent cover. You must have seen, no, it is encapsulated with a transparent cover. Okay. So now how is that, what is the principle of LED? What is the principle of LED? So it is forward biased, isn't it? Okay. So what will happen when the diode is forward biased? The diode is encapsulated with a transparent cover so that the emitted light can come out. This is simple. So when the diode is forward biased, electrons are sent from N layer to P layer, isn't it? See, actually in N-type semiconductor, where the electrons are located? In the conduction band, isn't it? Correct? This is conduction band. Higher level. All the free electrons N-type are in the higher level. Whereas in P-type semiconductor, where are the electrons located? Huh? Where are the holes located? Holes are always in the valence band, correct? Am I correct? Holes are always in the valence band. So under forward bias, this is a forward bias. Electrons are moving and it is falling to the hole now. Electron from higher level is jumping to the lower level. Am I correct? Correct? Are you able to understand? So electron is in N-type, electrons are in the conduction band, higher level. P-type, holes are in the lower level. So when electron is jumping from higher to lower level, what is happening? Electron, it is falling into the hole now. Energy difference, no, the electron is losing energy. So that is only emitted as radiation. That is the principle of LED. So when a diode is forward biased, diode is light emitting diode is forward biased, the electron is sent from N layer to P layer. Okay. So when the electrons are falling into the hole, the energy is liberated. The energy is radiated. That's why LED you get light. Okay.
So we can,
so,
for fabrication, we can use semiconductor, ma'am.
Fabrication. Huh?
Fabrication of LED, we can use semiconductor, ma'am.
Yeah, you can, but now we don't. Another question: pure semiconductor we cannot use if you want a visible light. Why? In order that LED, see, light is emitted. The light can be in UV region, Light need not be visible always, no. See, for emitting visible light has energy between 1.8 to 3 electron volt. Okay. So if you use silicon or germanium, it is only 1.7 electron volt for silicon and 0.7 electron volt for germanium. Okay. So if you have a silicon and germanium as a material, as a semiconductor element, can they emit visible light? They can emit light 1.1 electron volt or 0.7 electron volt.
Less than 1.8.
Less than 1.8. So visible light cannot be emitted. Maybe infrared. That LED can emit infrared.
We can't use semiconductor.
You can't use elemental semiconductor. Whereas compound semiconductor like gallium arsenide, GaAsP. That's why we are using GaAsP. Okay. Compound semiconductors are used. Okay. So now LED that can emit red, yellow, orange, green and blue light are commercially available. They have a band gap of, see, spectral range of visible light is this much. The energy corresponding to this wavelength is 3 electron volt to 1.8. So the compound
ma'am, we can expect from the colors, color based question, ma'am. Color based.
Color based, they won't ask. They will see why silicon or germanium is not
Carbon.
used to make LED, visible LED. Okay, because the band gap of silicon and germanium is less than 1.8 electron volt.
Because
in order to
no, ma'am, our syllabus is coming now for different colors.
that they won't ask. Whatever information not given in the thing, they won't ask. Maybe, see, it is given. They may ask. See, for use for red light, gallium, see, all are made up of this mixture only. Gallium, this compound, GaAsP. GaAsP is used for making lead of different colors. So far, they have not asked that. See, this proportion, they need not remember. GaAs 0.6, P 0.4. The energy gap is 1.9. Red light GaAs, GaAs only. Energy gap is 1.4 is used for making infrared LED. Infrared LED, if they have an energy gap of 1.4, it is enough. See, the most popular question is why we cannot use silicon or germanium to make LED that emit visible light. So the answer is
including carbon.
Yes.
Including carbon.
Carbon is not a semiconductor at all.
Okay.
We don't even use carbon. Silicon and germanium intrinsic semicell. Maybe silicon is used to make infrared LED. 1.1. Okay.
Okay.
So to emit visible light, the energy gap should be between 1.8 to 3 electron volts. So compound semiconductors are used. Okay. And advantages. Advantages students will know. Low operational voltage, fast action, bandwidth of monochromatic, long life, fast on-off switch. And they may ask this graph characteristic. So forward characteristics for each color. See here. No, this is a knee voltage, isn't it? This is a energy required, minimum energy required. Okay. So this is the energy voltage, but the x-axis voltage is not so correct. Maybe 1 volt only. No, energy gap is E into V, electron volt. So infrared, red, amper. See, for white LED, the energy required is much higher. The band gap should be larger for green, blue, and white. So next is photodiode. So what is a fabrication? Again, fabrication is, it is made up of photosensitive semiconductor material. Photosensitive semiconducting material. The diode has a transparent window to allow light to fall on the diode. Okay. And it is operated under reverse bias. Please ask the students to learn the diagram. Always you should have a resistor to resist the, to reduce the current, or it's a safety resistance. It's in order that the diode doesn't get heated due to high reverse current. So what happens now? What happens when the light is falling? Light falls on a diode. what is the use of a photodiode? What is the use of photodiode? What is the function of photodiode? It is used as a photo detector. It is used to detect light of different intensity. Okay. So now when light is incident on a photodiode, what happens? Photoelectric effect takes place. So additional electron holes are created. Additional electron holes are created. So now, so this is a junction, P side, N side. Now light is incident. So now additional, suppose del N electrons are created, that is equal to del P holes, isn't it? Electrons and holes are created, which are equal in number. So this electron, so you know, near P side, negative potential, near N side, positive. So due to the junction field, the electron will, the photoelectrons which are created will get attracted and then they get separated like this. So when a reverse bias is applied, so what happens when you're applying reverse bias? The reverse bias, reverse current flows. And this reverse current, the reverse current is, you get different reverse current for different intensity, I1, I2, I3. So I3 is more than I2, more than I1. So I'm able to detect the different intensity light, the reverse saturation current. This one is current on the, so reverse saturation current, reverse voltage. So different the reverse saturation current is different for different intensity. So I'm able to detect the signal of different intensity. Correct? This is the principle of photodiode. So under light. So the condition is a photodiode can detect, so it can produce reverse saturation current. What is the condition? The light incident should be greater than the energy gap. The light which is incident should be, then only know. So you know that the thermionic emission work function, isn't it? Correct? So incident energy should be greater than the energy gap here. Then only electron hole will be emitted. Electron will be emitted. So when electrons are emitted, holes will be created, and the reverse current will depend on, reverse current will flow. The reverse current is proportional to the intensity of light. Okay, why do we operate a photodiode in a under reverse bias? Why? That is a very popular question. Because the current in the forward bias is more, no? Then why do we operate under reverse bias? Anybody?
The change in minority carrier is easily measurable. It is more dominated.
See, if you take an N-type semiconductor, okay, due to light, the number of electron created is equal to number of holes. Correct? For N-type semiconductor, majority carriers are electron. N is more than P. But if you take the fractional change, del N is, suppose 10 electrons are created, not 10 holes are created. Okay. If you take the fractional change, del N is equal to del P, but N is more than P, no? So del N by N is less than del P by P. So fractional change now, with see, as intensity of light changes, I want appreciable change in the current. But fractional change in majority carriers is less than fractional change in minority carriers. Okay. So for, if you see, for different intensity, if you forward current, if I operate photodiode under forward bias, I may get a graph like this. So this, from this graph, I don't get a distinct value of current. If the intensity is more now, the current should be more. The current should vary. With respect to change in intensity, the current should vary. If I get a graph like this, I may not be able to distinguish between high intensity light and low intensity light, because fractional change in majority carriers is less compared to fractional change in minority carriers due to light. Whereas for different intensity, I'm getting different saturation current. So the saturation current is this much here. So it is easy to detect change in current due to change in intensity of light if photodiode is operated under reverse bias. So it is easier to observe change in the current with change in light intensity if a reverse bias is applied. This photodiodes can be used as a photodetector to detect optical signal. That's all. This, the children, you should write this. It is easier to observe change in the current because photodiode, what is the purpose of photodiode? To detect optical signal. Are you convinced, teachers? Yes?
Ma'am?
Correct. Yes or no?
Yes, ma'am.
Yes. And ask them to learn all the characteristics here. And this is an example question here. And you know the solar cell. You have a P-type slab, N-type slab, electrodes, top surface. We call it as a metallized finger electrode, and bottom. Again, a back contact. And then light is incident. What are the three processes that get initiated? Generation of electron hole when light is incident. So it is a photovoltaic cell. So children should not draw a battery. This itself is going to act like a battery, isn't it? So the process that gets started as soon as light is incident is generation of electron hole pair. Here also H nu should be greater than Eg. And separation. How do they get separated? Because of the junction field. There is a depletion region. No. So definitely electron will get settled near the N region. And holes will get settled in the P region because they find this as negative potential and this as positive potential. So they get separated. So once they get separated, what will happen? So electrons are here, holes are here. So the electrons will move to the inside. Electron will move to the inside and P will move to the holes will move to the P side. So the charge gets separated, that creates a potential difference. So when you connect a load, current will flow. Okay. So the electron will reach the inside and collect by the front contact, and holes will get collected in the back contact. Here there is a metal contact here. Contact. So electron, there's a conductor. So electron will move here and holes will move here. And when you connect a resistor here or a load, current will flow. It's going to act like a battery. So three important processes: this generation, separation, collection. Generation is due to light. Separation is due to what? How they get separated? Due to the junction field. No. They get separated due to the junction field. Correct or not?
And the
Okay. So now, what are the criteria for material selection? Criteria for material selection is the material should have a band gap of 1 to 1.8, high optical absorption, electrical conductivity, availability, and cost effective. And this is a, see, you are drawing in the fourth quadrant. Why are you drawing in the fourth quadrant? The characteristics. It's a short circuit, open circuit voltage and short circuit current actually. Because you are not supplying battery, no, I'm not supplying, supply voltage is not there. This is going to act like a battery. So that is why it is drawn in the fourth quadrant. Otherwise, in the diode forward characteristics and reverse characteristics, we draw in the first and the third quadrant, isn't it? Because voltage, plus voltage, minus forward voltage, forward, reverse voltage. I choose this because there is no external power. When you connect the point, it is like, see, when you are connecting, no, when you are connecting the load, it is like short circuiting, positive and negative. So it is called as a short circuit current. It's called short circuit current, the open circuit voltage. So few problems, I thought they may ask problem like this. Assuming that D1 and D2 used in electric circuit are ideal. Ideal means there won't be any potential drop. The resistance will be ideal. That's what, there is no potential. The resistance, we take it as minimum. So what is the current flowing here? Which diode will contain? See, whenever diagram is given, check which diode is forward biased, which diode is reverse biased, which is forward biased.
One is forward bias.
D1 is forward bias, D2 is reverse biased. Under reverse bias, the resistance, D2 resistance will be very high. Will be very high. So what you are finding out? So the circuit is given, you should find out the value of the current flowing through 2 ohm resistor. So can I remove this? No current will flow, no. The infinite resistance, reverse biasing, the diode will offer infinite resistance. Now the resistance of this branch will be very high. So only the resistance 3 and 2 will be considered. So the total resistance is 5 and D1 has very low resistance. So the net current will be, I will be voltage divided by 5. That is 0.4 ampere. So answer the following question. Why is the current under reverse bias almost independent of the applied potential up to critical voltage? So you get a graph. Actually, when you plot a graph, you'll get a forward bias is like this and reverse bias will be like this. Very low, and for all voltage here, this is V, this is minus V. For all the voltage, the current will be almost same, and this is breakdown voltage. Because the reverse current is the current under reverse bias is due to minority carriers. Due to minority carriers. So increasing the voltage will not increasing the reverse current because the number of charge carriers available is very, very less. Okay, but at a very high voltage, the covalent bond itself get ruptured. Okay, and the huge number of charge carriers come out of the lattice, producing current, increase in current suddenly. Okay. So all this, see under what consideration view photodiode is fabricated. Fabrication is from a photosensitive semiconductor and provided with a transparent window. This question already we discussed. Even though the current in the forward bias is known as is more, why it is operated under reverse bias. Draw the energy band diagram of N-type and P-type. Please ask the children to learn all this. Okay, P-type semiconductor, N-type energy band diagram of intrinsic semiconductor, N-type and P-type. They should learn. Draw the VI characteristic of LED. State the advantage of LED lamp over conventional incandescent lamp. Write the factor that controls wavelength of light and intensity of light. What controls the wavelength of light in LED? So it has been asked in the exam. Wavelength of light emitted depend on energy gap of the semiconductor, isn't it? Correct? Am I correct?
Correct.
Yes. Intensity of light depends on this voltage, forward voltage. Sometime when you buy this LED lamp, if under low voltage, the battery operated, if the battery drains out, the light, the intensity of light will be very less, isn't it? Must have observed. Correct?
Yes.
So it depends on the forward voltage. This is the characteristic of LED. So you have to draw a forward characteristic, but see that the white, for the white, it is the energy required is more. So the knee voltage is little high for white, very less for infrared. Okay, so graphs are given here. Name the type of a diode whose characteristics are shown A, B. What is the name of the diode here? What is the name of the diode here?
Solar cell, ma'am, B.
This is solar cell, this one. So for this is a PN junction diode.
P junction diode, forward bias, reverse bias.
What does P and Q represent here? This is open circuit voltage.
Voltage.
Open circuit voltage. This is short circuit current.
Reverse current, we can.
No, not reverse current. The case of solar cell. If yes. I connect a diode, if I connect a PN junction diode with a resistor,
Yes, ma'am.
Okay, so current will flow. This is a current. So as you increase, see here, what happens is, as you draw current, so as the current increases here, the voltage decreases. Correct?
Yes, ma'am.
Voltage decreases as you derive current. See for this voltage here, this is as current, as voltage become less and less as current increases. 3 diode D1, D2, D3 are made of semiconductor having a band gap of this much. Which one will be able to detect light of wavelength 6000 Armstrong unit? So photodiode. So again, you should start from this 6000. So first find out what is energy Hc by lambda. So you just do the calculation. 3 into 10 power 8. I think I can do this calculation. 6006 into 10 power minus 7 into 1.6 into 10 power minus 19. Can you quickly find out and tell me this 1.1?
2 electron volt.
Huh? How much?
2 electron volt.
2 electron volt.
Around.
I think you will get around 2.01 or something, isn't it?
Yes, ma'am. Around.
2.01. 2.01. So you know that for a photodiode to detect, H nu must be greater than Eg. So this 2.01 is 2.5. Energy gap is 2.5 for D1. Can D1 detect this wavelength? No, D1 cannot detect. D3 also cannot detect. Whereas for D2, 2 electron volt is 2.01 is more than 2 electron volt. Only D2 can detect this. So students tend to make a lot of mistake. Now I've given for a pre-board examination, they just wrongly they understood. So they should find the energy corresponding to the 6000. That should be more than, and then they have to convert it to electron volt. That should be more than the energy gap. Then only that photodiode will detect. So D1 will not detect, D3 will not detect. Okay, now it's time. So I've given some question and answer. I'm going to forward this. So see this interesting thing. Explain the formation of, okay, in the figure given below, the input waveform is converted output waveform by a device. What is this device called? What is the device X?
Full wave rectifier.
Full wave rectifier.
Because output is.
Yes.
Yes, ma'am. Continue.
Huh?
No, ma'am. Continue, ma'am.
What will be I1, I2, I3 here? Which is forward biased here?
Forward bias first diode 1.
Diode 1,
B diode
3.
Diode 3.
What will be I3?
I3 is reverse.
Reverse bias. So I3 will be 0.
Yes.
So you can find out I4.
Only A and E.
I and D. So you can find out I1, I2, I3 you have to find out. So
Yes.
you can find out I4, you can find out I2, you can find out. If you add I4 and I2, you can find out I1.
Yes.
But along with that, you should also consider this resistor.